All right, so I'm going to talk today with my coworker Gabi about the OlmoEarth project that we've been working on at AI2. And AI2 is a Seattle nonprofit with the mission of basically trying to build these breakthrough AI solutions to solve some of the world's biggest problems. And we started this project from the standpoint that AI can do a lot uh, for the planet, and that there was some lack in terms of the existing uh, solutions that sort of existed out there. A lot of times there's basically this kind of mismatch between what the researchers, sort of the deep learning researchers or the really sort of technical machine learning researchers were working on, and the things that were accessible to the experts in particular domains. So the actual people working on, some of these problems in the field. And this sort of distinction that exists, we can build these large models and train them on these particular tasks, these data sets, but actually getting them into the hands of people who could use them, sort of these nonprofits, these NGOs, would have been really difficult before we started this project. For a number of reasons, a lot of the things that we're working on are kind of active areas of research. The machine learning involved isn't really a solved problem. There's no easy sort of pre-trained models that you can just sort of plug in and have work well. So there's a lot of active areas of research for a lot of these problems. All of this training, all of the infrastructure for these kind of things is very expensive. A lot of the nonprofits and people that we're interested in working with don't have access to thousands of GPU hours, et cetera. And even just the data itself, it's hard to kind of get access to download, to have the infrastructure available for processing this kind of data. So we really wanted to bridge this gap basically between where the research community is at in terms of what's possible with sort of cutting edge machine learning techniques, versus what we can get in the hands of people who actually want to use these models to make progress on some of these tough challenges. So that's where this OlmoEarth project sort of fits in. Our goal is basically to open up some of the availability, some of the power of these models to these partners that we have. And AI2 was in a really unique position sort of starting this project in that we already had some external expertise. We already had some external partners that we had been working with to start to build out some versions of a couple of these models, where we were doing things like processing geospatial data, or doing things like training machine learning models on data from partners. But what we really wanted was basically a unified solution where we could have one sort of large foundation model that could do a lot of this processing, a lot of this work in kind of a unified way, and then also building out this platform to make it accessible and make it a little bit more user friendly. So we strive for a number of different things in terms of how we were building this. We wanted it to be relatively open in terms of sharing not just our code, but also the data that we were training on, all of the evaluations that we were using, and how sort of this training happens. And in order to make it a little bit more easy for people to use and also just understandable, we didn't want some opaque black box. We wanted something that people could really understand, how these models were being trained, how they were being built, and also have the sort of peace of mind, the security that, if for some reason AI2 stops existing in, I don't know, the next couple years, for whatever reason, these models would continue to exist. These models could still be used by our partners. Not that we think that that's going to happen, but we have partners that have been burned in the past by getting locked into some particular system. And then, if that goes away, they all of a sudden lose access to something that they've based, some part of their workflow on. So we wanted these models to be available, even if, something were to happen to AI2 for some reason, or to give that peace of mind to our partners. We designed all of this to be very user-centered. So, because we had some of these existing partnerships and we brought in partners along the way as we were developing and creating OlmoEarth, we really wanted the focus to be on solving actual kind of real world tasks from our partners, kind of building something that could be used just right out of the box by them. And something that basically would traverse this full life cycle of the tasks that we wanted. So all the way from gathering data, training these models, fine tuning them, and then actually running inference, sort of this complete end-to-end solution. So the idea behind the OlmoEarth Foundation model is that it's this backbone that's going to be delivering a lot of this insight. And the platform is something that basically sits on top of this model that allows easy interaction with the foundation model itself and allows our users to basically bring in, their data. And in the platform, they can even do things like do this kind of data labeling tasks, et cetera, to produce data sets that then they can fine tune our foundation model on, and then also in the platform run that fine-tuned version of the model on new areas, on areas that they want to run inference on, and get that those results out of the platform. So at the core of all of this is this OlmoEarth Foundation model. And there are a number of things that we're thinking about when we were building this model. All of this is running on geospatial data as sort of a starting point. So we're modeling the world as seen by these different sensors and satellites. And as you probably know, there are a number of different sensors, a number of different satellites out there. We wanted it to be extensible. We wanted to be able to take in a wide variety of different sensor modalities. So it's very multimodal, multi-temporal as well, because of course we don't just care about a static snapshot of the world. A lot of times we're modeling things like changes over time. So we want to model how one particular region maybe changes over time, or just get information in this temporal domain to better model things like, for example, crop type often depends largely on signal that you see over temporal ranges as opposed to changes that you might see in the spatial domain. We want it to be flexible because when you're running models on Earth observation data, you don't always have all of the data accessible at any particular point in time. You might have cloud cover on a particular day. Revisit time for satellites can vary, so you might not have access to particular sensor modalities. We wanted a model that we could run flexibly in, a number of different possible scenarios. And we wanted it to be extensible so we can add, train on different modalities, different sensors. If, we launch a new satellite at some future date, we want to be able to add that in easily. And also we wanted this to be fine-tunable. A number of approaches have focused just on sort of the embedding-based paradigm, where you're producing embeddings for maybe the world or maybe some particular regions, and then training something on top of those embeddings. And while those that can be one avenue to get good results, we found that the best results you really need to be able to fine-tune the whole model for. And so we really wanted to focus on producing a model that could be fine-tuned on new data, and then getting that in the hands of our users so that they could bring in their data, train on it, and get really good results. So OlmoEarth is state-of-the-art for a number of geospatial tasks. And this is showing results on a selection of tasks across segmentation, classification, and detection. Although this is not, this particular chart is not for detection, because this is just on some KNN and linear probing tasks. But it's state-of-the-art across a wide variety of different tasks. And this is both when used for producing embeddings and running sort of basic models like KNN and linear probing on top of those embeddings, but also for running fine-tuning across a wide variety of models as well. And this is compared to a number of other foundation models in the space and compared across various research benchmarks. And also, as we were developing OlmoEarth, we were using a lot of tasks from our research partners as well. And using that in our iteration process so that we made sure that the model we were building wasn't just good on some, sort of smaller research tasks, but was actually useful for a lot of these real world tasks as well. In terms of training the OlmoEarth model, we have a large pre-training data set that we released as part of the OlmoEarth release. Has a few 100,000 locations, a number of input satellite modalities, Sentinel-1, Sentinel-2, and Landsat. And then we also use some sort of downstream maps as well for training, things like world cover, OpenStreetMap, et cetera, as part of this pre-training process. And for pre-training, we're training on 12-month on a 12-month temporal range with samples basically every month. So up to 12 time steps sampled basically monthly. And the modeling that we're doing for pre-training is a version of basically masked image modeling with some modifications. This is a simplified view of it, but the basic idea is we're taking our input modalities, we're projecting them into token space, we're masking those tokens, and then we have an encoder-decoder style architecture based off of vision image transformers that we are encoding these tokens into some encoding. We're running our decoder on that encoding to try to basically predict what those masked tokens were and using a contrastive loss to try to get those predictions to be as close to the original tokens as we can. So this is the training for the pre-training for our foundation model. And for more details, definitely I would check out the technical report. And if you really want to delve into things, all of the code is also available on GitHub. So this foundation model is designed to fit into this larger platform that we're building. We've built this foundation model, but our users are these nonprofits that maybe don't necessarily have a ton of technical expertise. And that's why we built the platform to sort of sit on top of all of this and provide users with a nice interface to actually be able to start to access some of these insights from their geospatial data. So the platform itself, again, you can go through basically this full machine learning pipeline of finding a bunch of points in your geospatial data to labeling those data points across different categories for things like segmentation or classification or detection, fine-tuning a model on this data that you've labeled in the platform, or if you don't want to label data in the platform, you can bring in sort of external sources of data and upload them to the platform as well. Once you have created your labeled data set, fine-tune a model on that data set, you can define areas to run inference on and then get back the results all in the platform or export these results to, you can, sort of download, export these results as well if you want to, do your own processing on them after the fact. This OlmoEarth platform, we've been working on for just the last 10 months. So we've actually, done a lot of building of this entire platform in a relatively short amount of time. There are a number of different components to it. The foundation models being one sort of piece, OlmoEarth Run being our API for basically doing these inference type tasks, versus Studio, where we can actually do sort of these fine tuning of the models, and a number of other components as well. So it's this relatively full featured platform that isn't just about sort of the foundation model, but actually about data collection, data curation, quality assurance, things like that, fine tuning these models and delivering the results to our partners. And the idea behind all of this was there's just a lot of engineering challenges. Even if you have a relatively performant foundation model, that's not nearly the end of the kind of process for getting these things working on some particular new task. The engineering challenges even are just like getting satellite data from wherever you happen to, like, downloading a Sentinel-2 image, getting it from planetary computer, like getting multiple Sentinel-2 images across some time frame and making sure they're aligned, and trying to figure out, sort of what you need to solve a particular problem can be a very hard challenge. So we wanted to basically abstract all of that away from our partners, and solve a lot of these engineering challenges for them so that they could focus on, sort of their area of expertise. And a lot of this, DevOps stuff isn't necessarily the most glamorous sort of problems to solve, but it means that the partners that we're working with don't have to worry about, you know, what version of PyTorch they're running their particular model on. They can use the platform to abstract all of that away and really focus on, what the data is that they're bringing and the expertise that they're bringing.
Cool. Thanks, Joe. I'll take over from here. I'm Gabi. So yeah, Joe kind of introduced the platform and what we've built. And now I'll talk a little bit about how we're taking everything that Joe just described and putting it in the hands of people who are solving big challenges and making sure that it's useful for them. Next slide, Joe. So we're working with many partners already. As Joe mentioned, this is a relatively young project, but we've been lucky to already been able to work with loads of really awesome people. We're partnering with folks at both a global and a local scale, covering lots of different applications, as you can see here. And in the next few slides, I'll discuss 3 of those applications: agriculture and food security, ecosystems and conservation, and finally, wildfire and forest management. Starting with agriculture and food security. Next. So we've been working with CGIAR and IFPRI to conduct crop type mapping efforts in Nandi County in Kenya. So specifically, this consists of mapping different crop types and trees. You can actually see the legend in the top right over time and space. This is important to assess how food secure a region is and also to anticipate the impacts of anomalous weather such as droughts. So for instance, if you know where the crops are growing, then you can look up what the weather in those specific areas is going to be. Is it dry? Is there lots of precipitation? How does this compare to previous years? What were those yields in previous years? This kind of information. Next slide, Joe. So using the OlmoEarth platform, we generated annual crop type maps of Nandi County. Since we can easily generate maps on our platform, this means that we can also easily generate annual maps. And this is really important for assessing changes over time. So we have 2 examples here. On the top, where we can see the expansion of coffee and sugarcane to cash crops, and also in the south, on the bottom, a reforestation effort in South Nandi Forest. Another really neat thing about having an end-to-end platform, not just a foundation model, is that it makes corrective labeling much easier. So in this particular case 2, Ya Wen, who led the effort, noticed that there was confusion between tree and coffee classes. And so she was able to go into the OlmoEarth platform, do some corrective labeling, and then significantly improve the model's ability to discriminate between trees and coffee. So that's an example where having an end-to-end platform unlocks performance capabilities that are not possible if you only have basically a set of model weights. Moving on to ecosystem health. So we've been working with Global Mangrove Watch to map mangroves globally. Mangroves are carbon stores, and they're crucial in protecting communities from erosion due to storm surges, but they're also rapidly declining. So Global Mangrove Watch has witnessed a 70% reduction in mangroves. The way that Global Mangrove Watch currently works, they need to collect lots of labels to expand coverage of their maps. So they currently cover 50% of the globe, and they would like to cover the whole planet, but they basically need a more data and compute efficient approach because they can't double their labeling effort. It's not feasible for them to take what they've already done and then repeat it once more to go from 50 to 100% coverage. Using OlmoEarth, we can outperform their existing approach with a tiny fraction of the labels. So going from about 6 million training points to 10,000, we can match their performance. And so this makes global coverage a possibility for Global Mangrove Watch. Next slide, Joe. As in Nandi County, uh, we care about changes over time. So being able to make maps at scale over time is critical. So here we can observe when and where mangroves are being lost. This particular example is in southern Nigeria. And knowing when and where mangroves are being lost allows us to then confirm that the event happened using optical data. And then, which is another thing that's really important for Global Mangrove Watch, is start to interpret what's driving mangrove losses in different areas. So why are mangroves being lost in West Africa? Why are they being lost in Asia? What are the different drivers? The last application I'll discuss today is wildfire and forest health monitoring. Actually, this is two applications disguised as one. So first, I'll talk a little bit about wildfire risk assessments at scale and affordably. So in this project, we estimated live fuel moisture content. So this is an estimate of how wet vegetation is. And drier vegetation, so lower LFMC values, are correlated with an increased risk of wildfires. Typically, obtaining LFMC values requires in situ sampling. This is super expensive and time consuming. And so combining foundation models like OlmoEarth with remote sensing data allows us to make wall-to-wall LFMC estimates. So instead of having a few samples where you've been able to send people, you can understand the trends over space and also over time. So how does this change month to month? These are important to manage wildfire risk, to understand how controlled burns might evolve, and also during an active wildfire to see how is this active wildfire going to play out. For our second forestry application, we've been working with the Amazon Conservation Agency, and what they want here is an understanding of the causes of deforestation. So specifically, we witness a deforestation event. This might be measured by a tool like Global Forest Watch, and we'd like to quickly be able to assess what caused the deforestation event. So was it caused by landslide or agricultural expansion, for example? We're not the first to do this. On the left is an effort by DeepMind and the World Resources Institute. This defined deforestation causes at a kilometer resolution updated annually. And using OlmoEarth, we're able to massively increase the resolution at which this happened. So we increase the spatial resolution to 10 meters from a kilometer and provide predictions within a week of the deforestation event happening, as opposed to annual updates. And this allows the ACA to do much more fine-grained and timely analysis of causes of deforestation. So what have we learned, both from building this foundational tooling and deploying it along partners in the real world? So firstly, the goal of OlmoEarth is to allow impactful organizations to turn Earth observation data into actionable insights. And this means that organizations have to be included from the get-go. We can't do our R&D in isolation. Secondly, being fully open, as Joe mentioned, this is one of the key components of the OlmoEarth platform. This is a huge advantage to developing successful partnerships because it gives organizations confidence, as Joe said, that they can continue using our tools even if we stop working directly together, and it makes them more open to sharing their data with us, which in turn allows us to build better models. And finally, even though we want good models, as Joe pointed out, good models are not the only barrier we need to overcome to get tools into the hands of partners. And so besides the machine learning team, which is what we've been focused on in this presentation, there are tons of people involved in making the OlmoEarth platform accessible and possible. So this is what we've done so far. What do we have planned for this year, for 2026? So yeah, as I said, one of our principal goals is to get these tools and this platform into the hands of users. So to this end, we're continuing to engage with organizations to deploy OlmoEarth. Actually, since our November 4th release, we've had a higher level of interest than we anticipated. So we're working through this backlog of inbound interest to continue figuring out good applications and deploying OlmoEarth. In addition to these additional applications, we're thinking about what future improvements to the model and platform might look like. So one of the big areas we're thinking about is extending what's captured by the model. So to be more precise, can we extend the modalities and systems that OlmoEarth can reason about? This requires changes across multiple dimensions. We need to capture very different spatial scales. The spatial scale of weather is different than the spatial scale of Sentinel-2 data, temporal scales, and also modalities. And all of these modeling extensions that we're thinking about are directly informed by requests coming in from our partners. So for instance, partners who want yield forecasting, this requires us to think about large spatial scales, and also forecasting into the future, landslide prediction, or severe weather impact estimation. Next slide, Joe. So this slide's illustration basically demonstrates what I just said. We're happy with OlmoEarth v1, but we have a long way to go before we have a true foundation model for the planet. Yeah, thanks. That's all from us. I think we'll pass over to Chris now.
Thanks, Joe and Gabi. And we will save the questions until the end. And so if you have any questions for Joe and Gabi, please put them in the chat. And next will be Chris from the climate modeling team. Chris.
Okay, well, I'd like to continue this thread by talking about AI for predictive Earth system modeling, meaning both weather and climate and all the timescales in between. And the interest here is, of course, both in furthering science, but especially furthering our ability to deal with the impacts of weather and especially a changing climate. AI2's climate modeling team is also a part of our environmental effort at AI2. We're not fully integrated yet into OlmoEarth, but there is the goal to coordinate these two areas more closely as we develop both of them further. Our specific goal is to use AI to make faster, better, and easier to use climate models, especially for timescales of decades to centuries, but also giving information about extreme weather in a changing climate. We work to produce more impact by directly working with climate modeling labs, in particular NOAA's Geophysical Fluid Dynamics Lab and DOE's Lawrence Livermore Lab, both of whom are very active developers of climate models. We also collaborate with NVIDIA and another philanthropic project called M2 Lions. So all the stuff presented here is not mine, but basically produced by the group shown below, my team, in collaboration with these external groups. So in order to think about AI for weather and climate modeling, it's important to recognize that physically based weather and climate models are already very good. And so how do we actually improve upon them? And some of the things that make them good have to do with flexibility and fit for purpose. So in particular, the Earth system is complicated, so they're based on modular components. All of those components are formulated in terms of physical and empirical relations, which we hope generalize across climates. Climate is simulated as the statistics of weather interacting with similar ocean variability, land and ice. And so this enables seamless prediction where we're able to simulate the Earth system on all time scales from hours to centuries and millennia. So this is very useful for impacts assessment. In some sense, this flexibility to deal with a whole range of problems is somewhat analogous to AI foundation models. And so the question is, well, can AI actually match and improve on these characteristics? Now, AI-based weather forecasts have already taken over as the state of the art. Unlike physics-based models, they're not trained using physics, but they're trained using reanalyses, which are based on physically based climate models, such as ERA5. One way that they can improve on conventional forecasts is that they're way, way faster. Another one is that they have higher skill. So for instance, the plot on the right shows a typical measure, the root mean squared error of 500 millibar height, averaged globally as a function of forecast lead time. And the blue AI-based model is better, lower, in error than the black state-of-the-art physics-based model. These models use a variety of architectures. They all feature an encoder-decoder type architecture where they take the whole atmospheric state, they encode it into some set of latent variables. There's some representation of both horizontal exchange of information and vertical grid column exchange of information goes into a decoder. And that process is auto-regressively stepped forward in 6 to 24-hour steps usually. Now, if you try and extend these weather forecast models to longer timescales, some of them work better than others. Many of the most skillful weather forecast AI models are actually terrible if you try and take them out to climate timescales. So this picture shows a year, and what's shown here is as a function of latitude, the 500 millibar height, from ERA5, that's in this case the truth for this year, and forecasts made with different models going out all the way to a year. And you can see that for several models, Pangu and GraphCast in particular, after a week or two, they actually degrade and make very poor predictions, while the models at the right, DLWP and SFNO, actually stay on the rails much better. We actually don't understand what it is that makes some of these models do better in terms of longer climate skill than others, but obviously these are good candidates for trying to transform into climate models that can be run for decades longer. So that's what we try and do. The weather forecast models have only the most rudimentary representation of other Earth system components than the atmosphere. So typically they might predict only the near surface air temperature or the surface temperature of the ocean or land. So they're not really trying to predict the whole Earth system. And in particular, since the other components of the Earth system that have much slower timescales that carry the memory of, if you want, of climate, these models aren't really fit for that purpose. So some AI-based models now include a multi-level AI ocean for El Nino forecasting, typically highly simplified. But the real goal here, if you want to look at longer timescales like we might want for climate projection, is to try and surpass the bar for CMIP, the Coupled Modeling into Comparison project, which delivers projections for the IPCC reports. So this means multi-year climate stability and accuracy, ability to simulate coupled atmosphere-ocean variability, not just the atmosphere, generalizability across the past and into the future, and hopefully do something that that existing Earth system models can't do. For instance, by being much faster, being able to run large ensembles. There are a couple of different architectures that are used. One is a hybrid architecture, where machine learning replaces parts of the atmospheric model, for instance, the physical parameterizations, or full model replacement, where we replace the entire model by machine learning. And for training, we can either train the model using what I'll call here historical emulation, where you train the model on historical global reanalysis like we do for weather forecast models, or we can train the model to emulate an existing climate model. There, the goal is not to make a more accurate forecast than the climate model, but do it way, way faster. There are a couple of other noteworthy efforts that I wanted to point out other than our own. Neural GCM from Google Research was one such effort. It's probably the state-of-the-art hybrid model where the flow solver is based on normal computational fluid dynamics, but written in a machine learning friendly language called JAX. And here, what the goal is to learn just the physics, the physical parameterizations, but do so from the result of the model, from learning from reanalysis as opposed to from first principles. And this model is able to make accurate weather forecasts and is able to represent the historical evolution of climate over the last 40 years, although it does suffer with problems of stability. Another model from my colleague Dale Duran at the University of Washington is called DLESIM. It uses different architecture. It's a full model replacement trained on ERA5. Noteworthy here is that it couples to a simple upper ocean representation and can be run stably over very long periods of time, hundreds of years. It's trained and designed for the current climate. It can't handle climate change right now. It simulates coupled modes of variability like El Nino, but is much too weak. Our entry into this particular game is called ACE, the Ai2 climate emulator. Again, our goal is on longer term climates. So one thing we do that other models typically don't do is train on climate model output over a diverse range of climates so that our model is actually trained to handle the range of climates that we are likely to see in the future and have seen in the past. And because we do this and because we have a ground truth in the climate modeling, we can rigorously test the generalizability of our model to unseen climate scenarios because we can run those in the reference climate model after the fact. So we started simple and we've made things more complicated. We started with trying to get the annual cycle of climate right. And then we added now historical change in ocean surface temperature, CO2 changes, and coupling to slab ocean and now dynamical ocean. Our architecture is similar to other models used for weather forecasting, but differs in some respects. We use what's called the spherical Fourier neural operator architecture based on breaking all the fields into spherical harmonics where the learning is done. An important thing that we do is predict a lot of fields relevant for surface and top of atmosphere energy and moisture exchange, such as radiative fluxes and precipitation. We use a 6-hour time step, 1 degree grid, and 8 vertical layers. So one of the early things that this model showed it was able to do, which surprised us, was that although the model is only trained to make 6-hour forecasts, it actually does a great job on the mean climate. Maybe that's not so impossible to imagine, but also more surprisingly, it does a very good job on extreme weather events. So for instance, this is the PDF of daily precipitation over all grid points compared to the model that it was trained on, in this case, a DOE model called the EAM, which is part of the E3SM. And you can see out to the most extreme precipitation, the emulator, ACE, is reproducing the frequency of extreme precipitation quite well. We, like Neural GCM, are able to handle the changing climate that's occurred over the historical record as recorded by ERA5, if the ocean temperature is specified. So the blue of 3 different realizations of ACE that differ only in the initial condition, and the black is ERA5, and you can see that in general, the trend is represented in much of the interannual variability, which is due to El Nino variability, and the sea surface temperature is also represented. The advantage we have is that we can do these simulations at 1,600 years per day, which is very fast. And ACE not only produces the right amplitude of variability, but also the right pattern of variability in response to El Nino. So this is the surface precipitation pattern in response to a change in El Nino measured by the so-called Nino 3.4 index. And if you compare ERA5 in the lower right with the emulated response in the upper right, you'd be hard pressed to tell the difference. And climate models have struggle a lot to produce this quality of representation. As a result of this success, we actually also have an increasing group of external users, both the UK Met Office, which has been experimenting with our model for seasonal forecasting, and academic users as well, looking at various aspects of climate through the lens of our model. One thing that we've recently been doing is looking at how we can use a kind of global atmosphere model that's kind of amazing, kilometer scale global models, which represent the entire atmosphere on a grid of 2 to 5 kilometers. So we work with GFDL, whose X-Shield model has that character. And this is the cloud field, right, from X-Shield. You can see it looks indistinguishable from a satellite picture. You can see tropical cyclones and a lot of other cloud features. They're amazing if you've looked at climate models, which have much coarser resolution and blur these things out. But these models are incredibly expensive. This model can't be run really for more than 10 years. And so the question is, could AI take a model like this and leverage it into a climate model by basically emulating its climate and weather accurately? And also, so then the approach that we've taken then is we take a 10-year simulation with such a model, we coarsen it in line to 100-kilometer resolution, which is going to be the resolution of our emulator. We train our emulator based on this 10-year period. That's about as short a period as we can use. And we also train what's called a downscaling application to take the 100-kilometer simulation from the emulator and turn it into 3-kilometer output, again, using AI in the form of diffusion modeling. When we do inference, then we give it an initial condition, and we run versions of our emulator, which for this purpose is stochastic. And from each of those, then we can downscale to local scales, 3 kilometers. So here's an example. This is actually so that we could do a comparison, a 6-hour forecast using our ACE emulator. Shown at left, you could barely see that there is a tropical cyclone shown as a maximum in precipitation there. But the model knows enough about tropical cyclones that it is able to turn it in through the downscaling into a pretty reasonable representation of the tropical cyclone shown at right. Similarly, if you look at time mean precipitation, which is obviously important for climate, the original 10-year time mean precipitation is shown at right. You can see the mountain ranges of the Western United States here as precipitation maxima. What we do is then we basically train our coarse model, shown at upper left, to make forecasts of that. And the forecast is at coarse resolution, so it's a blurry representation of the precipitation. But if we add our downscaling module to it, it almost exactly matches what's at right. So that's comparison of what's in the lower left to what's at right. Another thing we've been working on is coupling to ocean models. So initially, we coupled our model to what's called a slab ocean model, which is a thermodynamic ocean model which can absorb or lose heat. And the main virtue of a model like that is it's very simple to compose and run. But on the other hand, it allows the coupled system to respond to changes in external conditions, such as CO2 concentration. So for instance, we can look at, well, what is the response of our emulator coupled to a slab ocean model to a change in CO2 as compared to a reference model on which we trained the emulator. And so the reference model, we just trained the emulator on a couple of climates, control climate, doubled CO2 climate, and a 4 times CO climate. And here we look at C for a 3 times CO2 climate, which is unseen. Can the model represent the warming that occurred relative to the original 1 times CO2 climate? And again, remember, the emulator is not trained on climate. It's trained to make 6-hour forecasts only. But nevertheless, it's able to represent the pattern of warming to a high degree of accuracy in this case. Most recently, then, we've been working with a team at M2 Lines led by Laura Zana, which is a Schmidt-Fuchs philanthropic project. They developed a full-depth ocean emulator, 19 layers spanning the entire depth of the ocean, which has a 5-day time scale. And we coupled this to our atmospheric emulator, which required quite a bit of technical work and challenge. Also required us adding an AI-based sea ice scheme. And what we did then is we trained these 2 emulators on a reference climate model run. In this case, a constant climate pre-industrial run of GFDL's CM4 model. So we trained the atmosphere model against the atmosphere part of the simulation, the ocean model against the ocean part of the simulation, and then we fine-tuned them to work together coupled. We tested the coupled emulator on the remaining 40 years of the run, and it's remarkably accurate. After a lot of work, we produce a climate with very small drifts in surface temperature from the original reference model. Drifts on the order of a fraction of a degree K in most places, which again is incredibly good. Model has an accurate sea ice climatology, the emulator does, similar to the original CM4 model in both hemispheres. And most notably, it is also able to spontaneously generate El Nino variability, which is, again, a tough problem for coupled models to do. The El Nino variability shown in orange is the emulator, and the black is the original reference CM4 model. So you can see that the emulator doesn't produce quite such large excursions of this El Nino index, Nino 3.4. But it does have roughly the right period, and it's much better than anyone's done before. Our ongoing work here is to try and make this work in the context of CO2 forced climate change. So in summary then, ACE, our emulator, is an efficient, seamless emulator of existing global atmosphere models or reanalysis. It's skillful in not only AMIP settings where we specify the ocean surface temperature, but also in settings where we use a slab or dynamical ocean and where we perturb the CO2 as well. It's easier and 1,000 times faster to run than an atmospheric physics-based atmosphere model of comparable grid spacing. And I demonstrated these 2 applications. HERO-ACE, which does downscaling, I think is very practical for the climate impacts community, and Samudra-ACE, which for coupled modeling makes it very important for the climate modeling and assessment community. Still a work in progress, but I think we've already made very exciting progress. And just like OlmoEarth, this is fully open in the sense of being open source code, data, model checkpoints, and development. So it's a model that the community can work with and modify as well as just use. Thanks.
Thanks, Chris. Excellent. We have quite a few time left for the conversation, for discussion. We already have a few questions in the chat. I'm going to just read them out. So if Joe and Gabi can also join us, and there are some questions for both teams. And the first team is actually for you, Chris. Awesome work. I'm curious about which climate model you are using to train the A's. Are you using this in addition to ERA5?
Yeah, so typically we train ACE on individual climate models or on ERA5. So we have a version of ACE that's trained on ERA5. We have a different version that's trained, for instance, on the atmospheric component of CM4, AM4. We have a different version that's trained on EAM V3, which is the atmospheric component of E3SM. The climate models that we work with are those that are from the climate modeling institutions that we partner with. We need them to run their original physics-based climate models to provide our training data, and we need them to customize those runs to provide that provide the training data in a form that we can use. So that's why GFDLs and Lawrence Livermore's models are the ones that we focused on there. But we also have experimented with fine-tuning from one to the other. And I think our goal longer term is to do a form of foundation modeling where we can train our model on a whole bunch of different climate models at once, and then basically flip a switch, basically give a label and have it look like any one of those or some optimal combination of them.
Thanks, Chris. Next question, I believe, is for Joe and Gabi. The question is, there has been many yield models focused on temporal forecasting, but deployments sometimes struggle with regional and sensor shifts. And how does generalization work in those scenarios when you have sensor or like regional shifts for those applications?
Yeah, I can start, Gabi. Maybe you can chime in too if you have anything else. But I mean, in general, yeah, we're thinking about this because this is a big issue, right? If you train your model just on one region, it's probably going to be hard to generalize to other regions. We've seen this with tasks like crop modeling or crop type prediction. If we train our model, just on North America, then it's not going to work very well if we're running it on regions in Africa, for example. So for one thing, our foundation model is trained on a pretty globally diverse sample, and hopefully that addresses some of this, just in that during pre-training, it sees a really wide variety of regions from all over the world. And then the kind of biggest way we want to address it is sort of empirically of a partner comes to us and they say they need results on some particular region. We're going to make sure that we have a good test set for that region and that we can give them some kind of estimate of how well the model is going to perform on a particular region. But I think one of the strongest parts of having this whole platform is the possibility of doing, as Gabi talked about, this kind of iterative deployment and training process where you train a model, you get as much data as you kind of can, you fine tune the model, and then when you run it, you can see the predictions. You can actually go in and sort of start to edit those predictions or relabel things that it gets wrong. So if you are trying to run predictions on some region that's totally out of bounds of your training data, maybe the model is going to make some mistakes, but then you can do some relabeling, retrain the model on those new labels, and hopefully just sort of improve from there. There's no magic that I know of to get around these kind of things, right? Like we're not going to be able to sort of magically get over the fact that like things are just going to look different in different parts of the world. Yeah.
Anything you want to add, Gabi?
Yeah, that was all. Nice job, Joe.
Thanks. Next question, I believe, come back to Chris. So the question is, does the model impose any additional structural constraints to stabilize the long horizon forecasts?
Yeah, so within ACE2, we do enforce a couple of constraints within our machine learning. They're enforced within the ML itself, not after the fact. And these are we impose global moisture conservation and global dry air mass conservation right now. These are actually not required for the model to be stable in long rollouts, but they do help. In particular, I think with our architecture, we don't actually find we have problems with blowups, but sometimes the model will blip into a poor climate for a while and then unblip and that's worse if you don't enforce moisture and dry air mass conservation. One thing we also have tried doing, and I think we'll probably try to do more in the future, is energy conservation. But interestingly enough, even physics-based climate models don't actually conserve energy that well. ERA5 conserves energy terribly, certainly on a time-step to time-step basis, because it's constantly trying to fuse new observations with an existing model. So in general, I think the most important ingredient is your basic architecture. Some architectures are just more stable than others. And so the process of natural selection is that those end up being better for doing weather and climate in the same model. And we happen to have lucked onto an architecture which was good.
Thank you. A follow-up question on that. Thank you for the answer. Is there a sort of balance that you strike between a sort of conservation, but also dissipating properties?
Right. Well, the model doesn't know anything about dissipation at all by itself. There's no sort of artificial diffusion. There's basically, I think the main aspect of dissipation that's important here is actually, what you think of yourself learning here is you think of climate as being the attractor of weather. So in the sense of dynamical systems, weather, the atmosphere is how the atmosphere moves, evolves from time to time. So weather is something you can actually predict. It's more or less what these models are being optimized to predict. And then you hope to get a good climate because you're progressing around the attractor that's sort of defined by the weather in an accurate way. And I think what does help is if you don't just give it the weather that we actually have, but you actually give it some samples that are a little bit outside of current weather, but which, for instance, a climate model might be able to make a prediction that's like going to force it to the attractor, and you use those to help your model be stable if it happens to drift a little bit outside of the weather it's used to seeing. But I would still say that, you can't think about machine learning based climate models using the same principles as using physics-based models. They have their whole own character and personality that you more or less have to learn how to work with.
Thank you.
I'm going to ask a question that has been proposed by the audience, which is that's for any of you. Have any of you tried to use the explainable AI methods to evaluate the reasonings and the feature selections in the applications or the outcomes of those, both ACE2 emulators as well as the OlmoEarth, the foundation model, because those has been used quite frequently in those non-foundation model settings to understand why the model performs certain ways.
Well, from the point of view of ACE, we've talked about it. Some of the people who've actually some of the academic users of ACE have started to try and use some of these methods. But I think the complication is the atmosphere represented at 1 degree resolution has basically more than 1 million degrees of freedom. Our model has 200 million parameters, and that's just a heck of a lot. And so far, explainable AI kind of gets a bit drowned in that scale of application.
Thanks. Gabi?
Yeah, I guess we're in a similar position where we've talked about it, but haven't really done anything much yet. One of the discussions we've had with some academic partners have been around whether we can recover like indices that we know are meaningful from the model or from embeddings. And so this might be one of the way to deal with the high dimensionality of the model and of the data, if we can recover things that remote sensing researchers are confident are meaningful.
Thanks, Gabi. I'm going to go back to Chris, and there's a specific question about what kind of downscaling approach does the Hiro ACE use, and what's the trade-off between inference times and accuracy when you're trying to do those high resolution downscaling?
Yeah. Well, originally we based our downscaling approach on a sort of stripped down version of NVIDIA's CoreDiff approach, corrective diffusion. So it's diffusion based down super resolution, basically. We focused on being simple rather than being super efficient. But we did need to be efficient enough to be able to do, say, for instance, a year's worth of downscaling in a fairly short period of time. So, for instance, we can do a year's worth of downscaling over a patch of the globe, 1,600 by 1,600 kilometers, which is large enough for most applications in 45 minutes. NVIDIA actually already knows how to use basically distillation processes to make even our approach probably 10 or more times as efficient as it is right now. In which case, I think there wouldn't really be much of a trade-off between inference time and accuracy. But right now, mainly our focus has been on achieving accuracy of downscaling. The one trade-off that we have made is more conceptual, which is what fields go into downscaling. So in dynamical downscaling, you basically run an entire high-resolution model to get out the surface fields you're interested in. Our precipitation downscaling approach was used only coarse resolution, precipitation, and winds, and nothing else.
Right. Thank you.
Thanks. Question for Joe and Gabi, the OlmoEarth, which I think is related to a previous question. So how do we make sure a model is robust when used in different environments? For example, if crop type classification models gets 88% F1 score during the testing, how can we ensure that performance doesn't change drastically once the model is deployed in a different real world settings for those applications?
So I'll assume, again, this is a situation where you're not confident that the test set covers your deployment setting, in which case I think it's hard to be confident short of validating this empirically. And this is something that we try and enable in our platform, so you can easily make maps, easily visually assess them, and then easily do corrective labels or some sort of stratified sampling strategy to do a new set of evaluation labels. But yeah, as Joe implied, we have a good model, but we're not magicians. We can't just arbitrarily generalize absent labels, and we can't arbitrarily be confident absent some sort of test or evaluation set.
I guess that goes to, I have a follow-up, which is that, is there any way that you can produce some of the uncertainty or in a way that tells the users about your confidence about that prediction in some ways?
Yeah, part of writing the paper for this was thinking about things like how do we calculate uncertainty? I mean, so you can do things like bootstrapping to at least have some confidence in how the bounds with which you might generalize to new data. And also you can do sort of like training on, one thing you can imagine is training on and testing on data from 1 year and then seeing how that generalizes to future years. Train a model just on 2022 data, for example, and then see how it performs in 2023 and 2024. And then that can give you some estimate of sort of uncertainty in future years. But obviously, like, in some particular year, you might have some event that just like you're not going to generalize to. We're thinking about how we can do things like generalizing or getting bounds for uncertainty in terms of generalization. But there's always things that can happen in the real world that can make that not necessarily hold.
Thanks, Joe. Hamed, you have a hand raised.
Yes, I'm just gonna follow up my question about the XAI methods. Just gonna put it out there. My PhD work is on XAI methods, mostly on climate predictions, and my use case is on downscaling for Florida for precipitation. And I'm currently working on a method that doesn't matter like how it does matter, but it's not that important how big your model is. Like 200 million is doable with the framework that I'm trying to work right now. And as I do it right now, I can test my models, my deep learning models for precipitation downscaling that actually can lead me to better variables. Let's be for error 5 or any other data set that we have to select better the options and see which part of the model itself reasons about what. So these kind of things, if it comes to your concern, maybe you can contact and we can have work on that. We can have talk on that. But it is something that I'm really interested in getting somewhere with it.
So, Hamed, we are about to release the code and the full training pipeline for the stochastic version of ACE2 and the hero downscaling, so that you could experiment with it if you want. Probably within the next couple of weeks. We've submitted an archive paper about that work, but we're right now putting it in for peer review at AGU Advances, and in association with that, then there will be a fully open pipeline that you're welcome to experiment with. It's unfortunately not possible for us to work too closely with individual people on stuff like this, just because we're a small group and we've already got our own development to do, but we are certainly really interested in hearing what you find out.
For sure, I can take advantage of that, but also can share my work to see if it's useful for you.
Yeah, and I think downscaling is interesting too, because although in theory, downscaling in any one region, involves data from the entire world. It's only data from a very limited region, which is really important.
Yeah, but you don't have to be worried about the place. It doesn't matter if it's climate. It's just a deep learning model helps me.
For sure. Yeah, I understand.
Thanks, Chris and Hamed. And I think we need to wrap up our webinar today. I'm going to ask a question inspired by the audience question to both sides. And I think the question is about what specific bottlenecks that has been underexplored in the questions for the ACE, the climate emulation parts. And so what's one of the bottleneck or the underexplored areas for the emulation? But I think that's also the other question for the OlmoEarth team is that what are the areas that could use more attention to in terms of creating those Earth observation foundation models for the more broad applications? Maybe Chris, do you want to take a step first on the climate emulation side?
Yeah, well, I mean, the elephant in the room of AI for climate modeling is that climate modeling is about predicting or projecting the future, which we don't know anything about, based on the information we have at hand, and doing it better, not just faster, but I would say better than existing climate models. And at this point, we do not have a clear strategy for doing that. We don't even have a model which is as good as an existing climate model, really, at doing that problem fully. And so, but that's what we would like to be able to do. And the question there, or the real challenge, is how do we fuse all of the power of AI, the data-driven power of AI, to take advantage of our knowledge about the present climate, with all of our physics-based understanding that is going into making existing climate models generalizable to future climates. How do you put together human expertise and data-driven AI expertise in the same model more efficiently?
Thanks, Chris. What about Joe and Gabi on the OlmoEarth side?
I've got opinions. Gabi can chime in also, but I think, and this is just sort of stuff that's on our roadmap basically, but Earth observation data has a huge variability in terms of relevant spatial and temporal resolution. So things in the weather happen on an hourly or daily basis, but things in the climate realm happen on a yearly or decade basis. Training models that can handle that variation. So like, can you have a model that is modeling both weather and climate, or modeling both in the spatial domain? Some things spatially you need quite large context. Are you looking at an ocean, or are you looking at a very small like saltwater lake or something? Those two things might appear the same if you have a very small spatial context. On a larger spatial context, they're going to obviously be a lot different. This can be true for a lot of different features. Some things, you need very fine resolution information, but some things you actually need a much larger context. So being able to process all of that with kind of a unified model is something that I've been thinking a lot about, and something that I think will help with a lot of the applications that we're looking at currently. I'm thinking in particular of ecosystem classification, which is something we're working on, where you would really want some larger context for solving some of these particular questions. A river that you're looking at, what particular kind of river is it, is actually answered better by the surrounding spatial context than by any particular information about the river itself.
Thanks. Gabi, anything you want to add?
No, I think that this is probably the most pertinent question that we need to answer, not just for ecosystem classification, but for instance, for yield estimation, where we care about very different temporal resolutions than monthly, which, as Joe mentioned, that's what we train OlmoEarth on at the moment. So how do we bridge spatial and temporal resolutions, I think is an interesting thing that we need to figure out.
Right. Thank you, Chris, Joe, and Gabi. And also I want to thank Patrick Bickman as well, who is on the call today, has been helping making this happen. And so thank you everyone for joining the webinar today. And we will make the recording available via our YouTube channel after the events ended. So thanks everyone for joining.